no matter which quadrant you are in, you can get both an expression for a vector that would be tangent to a curve and also a vector that would be normal to a curve, assuming you're working in a plane. So we'll go through that as soon as I distribute some more paper. So if you're thinking of curve traced by r of t is x of t comma y of t, remember we're in the plane, then this would be dr in differential form, dx comma dy. And you, as you know from chapter 13 really, when you have a position vector r of t, the dr dt is going to point tangent to the curve, and the dr dt over its magnitude is the unit tangent. So as a differential form then, this would point tangent because it's dr, where r is x comma y. So then in either chapter 12 or 13, when we were talking about tangents and normals, we established that if you have a vector that is constant length, whether it's a unit vector or not, then the derivative has to be, assuming they're not zero vectors, the derivative has to be normal. And so in the case of a vector in a plane with two components, you can also get the normal rather than by doing a derivative, by taking the two components in the reversed order and changing one sign. Because you see, if you do the dot product, dx dy, then here you'd have dy times minus dx, and the total would be 0. So if I look at the picture, you see that the first component here in the blue is pointing off to the left. So that means that at this point in the first quadrant, the dx here is negative, as I wrote. The blue is pointing upward, so the dy is positive. So then when you turn these around, what you have is positive, because it's the dy that from here that was positive, and you change the sign to get a vector so the dot product is 0. Well, the dx was negative in blue because it pointed left, so minus dx then is positive. So the two in orange are both positive value, which is up and to the right. You see, it's to the right with the first component and upward with the positive second component. So then you can check this in the second quadrant position. So your t, if it's second quadrant, you see it's pointing left and downward. So that means both of dx and dy are actually negative numbers for a vector that's pointing like that. And so then when you reverse the order, the dy here was negative, so it's still negative. Well, you see on the end it is pointing left, so the first component would be negative. And then if dx was negative here, minus dx is positive, so the second component is positive because it's pointing upward. So what I'm trying to say is that if you analyze in each of the 4 possible positions. If you will analyze what is the sign requirement for dy and dx by how the vector is pointing. So if it's pointing left, the first component has to be negative. If it's pointing upward, the second component has to be positive, like that, and so on. You'll see that it works out in all 4 cases. So look at the third quadrant. So your t, if you're coming around the circle, say, is pointed back toward me. So it's down and to the right. So that means in this one that the dx is positive because it's pointing to the right in the blue one, and the dy is negative because it's pointing down. See, in each case with the black, I've rewritten either what was in the blue or what was in the orange with what the sign actually is on your component, plus or minus, you see. So then when you reverse here, your dy, which was negative, is still negative. See, I'm saying it there. It's pointing to the left, so the first component should be negative. And then the dx was positive, so minus dx should be negative. It's also pointing downward, so your second component is negative. And finally, last but not least, over here, you see your tangent is pointing up and to the right, so those are both positive, which for some reason I didn't write, but you can see that, oh, yes I did, they're up there. Okay, and so then you turn that around, that was positive, so it's over here, so now your first component on the orange is positive, so that means it points to the right, and you see it does. And then the minus, when this was positive, would be negative. Second component negative, so it's pointing down. So we can always get, if we have a curve in the plane traced by a position vector, whether the curve's a circle or not, you can think of r of t as the vector, the tip of which traces your curve. You can do the differential dr, and that'll get you a tangent vector, and then you can reverse the order and make the sign change. And if you make the sign change on the second component, you'll get the correct, a vector that points correctly to be the outward pointing normal. If you had instead changed the first sign and not the second one, it would be an inward pointing normal. But for the purposes of the theorems that are in this chapter, we want the outward pointing normal. So with this understanding about how to write a tangent vector and a normal vector, we can put down the theorems that the first part of this chapter is trying to get to. And so we can talk first about what we call circulation integrals. And Stokes coined the name, and among the blizzard of paper, you see a little bit from Wikipedia about Sir George Gabriel Stokes, which you can read or not. You see his picture there. He strikes me as a person who thinks he's pretty good in that picture. But anyway, he taught, as I said yesterday, he taught at Cambridge for 50 years, more or less, and was one of the top people in 19th century mathematics, certainly, even though he wasn't Gauss, who, well, Gauss died when Stokes was comparatively young. Most of Stokes' work was after Gauss would have died, but anyway, so we're thinking of F as a field, which we talked about yesterday. Our word field means a vector function, which may be either with one of the three kinds we talked about yesterday. It can be a thing like the gradient, where the domain is a scalar, and then you do the gradient of a scalar function and you get a vector valued function. Or it can be what we called divergence yesterday, and the divergence, remember, is the del operator dotted with, I think I gave you the set of notes that talks about divergence and curl. So if you do divergence of a vector field, you get a scalar valued function. And then finally, if you do curl, as we said yesterday, you start with a vector valued function and you end with one. So we are thinking about what we call an oriented closed curve. So this issue of whether you can orient something is important in this chapter, but we'll, the book takes that issue up later in the chapter. So at least think about a closed curve, and you're going generally in the counterclockwise direction to make these theorems come out right. So this little symbol is to indicate that you're going in the counterclockwise direction around the curve, kind of like I've done here. So Stokes called an integral of this sort a circulation, or a circulation integral. Then we also have what are called flux integrals. Gauss named that for a field, and that would be in the plane, the integral typically taken in the counterclockwise sense of the field dotted with this outward normal. Here, you see, it's a little different letter, N. This would be F dotted with the unit outward normal, and then ds would be your differential arc length. And so you can also write it like this, F dot dy minus dx, because that's the outward pointing normal in all four cases. That's why we just talked about that, so I can use it here. So if you're in the plane and your field is a vector with components m and n, then your flux integral, you see it's the dot product of this vector with that one, so it's m dy minus n dx. So when you have a closed path that is enclosing a region R, then there are two Green's theorems, and you got the Wikipedia little biography about Green, and so there is the circulation curl Green's theorem, and there is the flux divergence Green's theorem. There are two of them. So the circulation curl is the f dot dr, but you see if your field is mn, and your dr is dx dy. If you do that dot product, if you do dot this vector with that, you get m dx plus m dy. Okay, and this itself is called flux density, and it turns out that the line integral around the closed path, the line integral worked like we were doing yesterday to work line integrals, equals the integral over the region. This is the region R that is enclosed by C of the curl of the field that is in vector form here, m comma n. It's curl dot k integrated over the area that's enclosed. And if you remember from yesterday, we have curl is del cross a three-component vector. If it's a cross product, it always has to be set up as a three-component vector or vector operator. So the components are m, n, and p, say, and we went through doing this yesterday, and this would be the first, second, and third component of curl. So the k component of curl is this. So curl f dot k, in other words, is this vector dot k, which would just give you this component here. So curl f dot k is this difference in the partial derivatives. So I have the integral over the region like this. So one of the two Green's theorems in scalar form then is this line integral called flux density is this double integral done in the sense of chapter 15 of the k component of curl integrated over the interior. Okay, we'll see this in section 16.4 next week. We'll have problems that are taking a field and showing that this and this give you the same thing, but I'm trying to give you an overview of what's going on here this morning. The other one of the Green's theorems is this one, the flux divergence. This dot product of the field with the outward normal is the flux integral named by Gauss, as I said. So this is the outward flux around the curve. Here it is, if you in what you could say is scalar form. Here's the same thing written as a dot product. If you do this dot product, you get that, in other words. And that equals the divergence of the field integrated over the region that's interior to the curve. And this is what Gauss called flux density. And so you can say the second Green's theorem any of these ways. You can say it entirely scalar, where you'd say this line integral is this double integral, and not even admit you know anything about divergence and curl. Or you can say it in a vector sort of way like this. So the circulation density then is the k component of the curl. And notice that it can certainly turns out rather, that the circulations, which are like this, which equal curl got from the normal, will be zero anytime that your curl is zero. Because you see, we're saying this integral that Stokes called a circulation is a dot product of a curl with a normal. So if your curl is zero, certainly this is the integral of zero. So that says sometimes circulation integrals, the integral around the closed path as a line integral will be zero, and some are not. So that gives us a test, which we'll work with in next week on Thursday in section 16.3 for when a field will have a zero circulation, as Stokes called it, line integral around the closed path. It will if and only if the curl is zero. So you can test a field and know about that. A vector identity that's important here is that if your field is a gradient, that's if and only if the curl of the field is the zero vector. So if you notice the one set of notes that I gave you, there's the one that's on the big paper, and it's printed, not the one with the picture of Gauss, the other big paper. It's printed on two sides, and on one side I've copied a couple of pages of the appendix of the back of your book. And you see there on the left, if you're looking at that side of the sheet of paper, it's vector operator formulas, Cartesian form, and it's you see down there vector identities on the left-hand side of the page, and the very first one you see is del cross del f equals zero vector. So that says the curl of a gradient is always zero as an identity. Has everybody found where I am on this? On the big sheet of paper? Okay, so let's see how you prove that. And so starting with a scalar function for which you can do the partial derivatives, your gradient is this vector in three-component form. So that's the field we're working with. So then just simply work out your cross product. So you have ijk, and then your partials, and then fx, fy, fz, and then repeat columns 1 and 2. And if you do your products on this slab, the blue, you see, for example, with the I, you're thinking you have a differentiable function, little letter f. So this means first you did a partial with z, and then you're doing the partial of that with respect to y. So that's fzy. Remember our work in chapter 14 with partial derivatives and mixed partials. And so if you're using the subscripts, the letter that's closest to the name of the function is the variable you used first, the partial derivative that you did first. So this means first partial with z and then partial of that with y. And that's what this is saying you're doing. So you already have the partial with z when you've entered your vector on the bottom line. And Then when you come back the other way with the I, you have this product, which means you have first done the partial with y, and then you're taking the partial of that with z, so that's f y z. Well, in chapter 14 we said that as long as you're talking functions that have the partial derivatives in both orders, that the order doesn't matter. So this is the same as that. So the blue and the orange are actually the same. And the same game is true for the other two columns. So what you have is something minus itself, actually. So you get the zero vector. So the curl of a gradient is always zero. This is an important concept in physics in general, and we'll use it at various times. So as long as the mixed partials are equal, the curl of the gradient is going to be zero, and we won't see anything else. So for fields where the curl is zero, the fields are gradients of something, and then what we will work with Thursday, next week, is if we have something, we start with a field, we take its curl, we find the curl is zero, then we know it's the gradient of something or others that you call some little letter f of x, y, z that you call a potential. And so we call the scalar function that you have the gradient of the potential for the field, which then is gradient of this scalar function. And in that special case where you have a field that's the gradient is some potential, a line integral from, like on a curve like this, not necessarily a closed curve, you have a curve that starts at some point A, B, C, and ends at some point J, K, L. The line integral from there to there on the curve will be simply the difference in values of this potential. So if you figure out what the function is that you have the gradient of, and if it turns out that the curl of that gradient is zero, then you can do line integrals. You don't have to parameterize. You can just take the difference in the values of your function little f at the endpoints like that. So this is a fundamental theorem of calculus for line integrals. So that we'll be working with that Thursday in section 16.3. So then, for example, you can define work as a line integral. Work in moving an object along the curve from point A, which is the tip of the position vector r that's tracing out your curve, to a point B, is the line integral along the curve that connects points A and B. And so you have various ways that you could define work then as a line integral. You see, the curve isn't necessarily a closed curve. It could be around a closed curve, in which case you'd have this symbol on your integral sign, but it doesn't have to be. You can talk about the work done moving something from one point to another along the curve that isn't necessarily a closed curve. So you can say work then is your line integral on the curve, whatever it is, f dot the tangent vector, this would be the unit tangent vector, differential arc length, which you remember is the magnitude of the velocity. Or you can say F dot dr, or F dot dr dt, or if you're thinking of your field as in component form, you could then your F dot dr in component form would look like this. Well, this is F dot dr dt. So this one in component form is that one, and this one in component form is that one. So we can interpret the line integral as work done, moving something in a field from somewhere to somewhere. If you have a field that is for which the curl is 0, then there is this potential. So gravitational fields are like that. So that means on a gravitational field on a closed path, the work done is 0. In other words, it means that if I do something like this, okay, so talking about the Earth's gravitational field. Okay, so after all that, well, how do you do anything? Well, now let's come to this end. And so if you look at what the homework would be in section 16.2, it's more of the same sort of thing that we were doing yesterday with parameterizing, working parameterized integrals. So, for example, in the problems 7 through 12 in 16.2, they're all 6 of those problems are talking about these paths from 0, 0, 0 to 1, 1, 1. You might go on the straight line, so we get that parameterized. C1 is the line segment that connects this point and that one in a straight line. So if you write the equation for the line that comes up like this, as we practiced yesterday and as you did in chapter 12, it'll be T, T, T. So call that path A. Then path B is in the rose-colored pen, curve C2, and they give you that X is T, Y is T squared, Z is T4. That's given. Then path C is a set union. You come out on this line down here in the XY plane, where this between my thumb and finger would be a 45-degree angle. So that's R3, which would be T, T, and 0. You see, this is really, that's the line Y equal X. So your Y is equal to your X right here. And then after you get to this point out here, you go straight up. This is 1, 1, 0, and that's 1, 1, 1. So your R4 then, tracing curve C4, X is 1, Y is 1, and then you're using Z as your parameter. You'd get the same answer if you just called it Z, or if you want to change it to T. And all of these are parameterized with T between 0 and 1. And your path C where this is A, B, and these, the set union here is path C. So look at problem 12. So what they want of us is that we work the line integral on path A, on path B, and on the set union here of these two, which is path C. And this is the field, okay? So if you're using path A, you see, then you're saying X is T, Y is T, so Y is T, Z is T, and then here you're saying X is T, Z is T, and then you're saying X is T, and Y is T. So here's your field parameterized according to the path you're on. When you go from one path to another to the third one, your parameterization is different, so your way you represent F is different. But it's always in terms of the parameter, it's always in terms of T. We were doing this yesterday, you recall. Okay, so then your integral on curve C1 is F dot dr1, which is this one parameterized, the line that's coming up like that, really, dt, dt. So first of all, notice when you've done this, you have 2t all the way across. So you can factor the 2 and you have t, t, and t. So this is same as that. And then with this being your R1, your dr dt is 1, 1, 1, derivative of each of the components, right? So that's there, dr1 dt, and then you're integrating with t. So do your dot product, and you see in this case, you get t plus t plus t, you get 3 of them, and you're integrating that 0 to 1, which is math 170, and put in your limits and you get 3. So that would be the work done, if you want to interpret it that way, moving something from there to there on that path, okay? So it could be foot-pounds, or it could be joules if you're metric, whatever, okay? Now, path B. Path B, remember, you have this parameterization. So going back to your vector, your y is t square, your z is t fourth. So that's how I get, well, it's here, t square plus t fourth. That's how I get those. Then, next component, x is t, and z is t fourth, okay, there. And then finally, third component, x is t, and y is t squared. So you see, I have to rewrite my vector each time using what path I'm on. Then that's the vector on that path. It isn't the vector anywhere but on that path. And then I need the dr2 dt. So again, here's my r2. I do the derivative, and so I have the 1. And then from t square, I have 2t, and from t fourth, I have 4t cubed. And then I dot this out. So I have t squared plus t fourth times 1, and then I have t plus t fourth times 2t, and then I have t plus t squared times 4t cubed. Okay? So there's my parameterized dot product, my expression for the work, if you want. You could say this is a function work in terms of the parameter t that's correct for this field on this curve. Okay? You can begin to see maybe the point of the Green's theorems over there, which are allowing you to replace doing things parameterized by something that instead will be a double integral over a region if you're going around a closed path. However, you still have to know how to do this, because the Green's theorems over in the center of the room work only if you're going around a closed path, you see, and you may not be on a closed path. These aren't if you're thinking of them individually. Okay. So anyway, you do your dot product here. So then you do your algebra and you collect your terms, okay? And then you integrate, which fortunately is straightforward at least. You don't have a U substitution or anything. And then you put in your limits and you get 3, which ought to make you suspicious of something. You took this path and got 3. You took this path and also got 3. So you might hazard the guess that you're actually dealing with a field that's independent of path. Okay, for which, if you were following what I was saying over there, you have a way to test, right? If it's independent of path, if and only if curl is 0. So we could take the curl of this thing and see whether or not it's 0. If it's not 0, then it's just a happen so that these are the same, and we'll find another path where they're different. If the curl is 0, we could play this game for the rest of our lives. Hopefully you have something better to do with your lives. But if we played the game, we'd always get 3. Well, let's go ahead and try path 3 first, path C. So we have then the R3, which is the line down here on the floor at a 45-degree angle, which is t, and 0, and then we have dr3 dt, which is 1, 1, and 0. And so then going back here, you have t plus 0, which is just t. You have t plus 0 again, which is just t. And then x plus y, each of them is a t, so you have 2t. So then you do the dot product of this vector with the dr3, and you see when you do the dot product, you get t and 0, so you get t plus t, or 2t. And then you integrate that, which will give you t squared and give you 1. Now that's the work, if you want to say it that way, going from here to here. And now let's see what it takes to lift straight up, like that. Well, that's path C continued, you see. So your R4 is 1, 1, and t, and your derivative is here. So if you parameterize, you see you have 1 plus t 1 plus t, and then 1 plus 1 for your third component. Your x and y, when you're going vertically here, are always 1 and 1. And so you do the dot product here of the parameterized f with the dr dt, and you have 0 plus 0 plus 2, 1 times 1 plus 1, which I have here. So you integrate that and you get 2, and then you, when you have a path that's a set union, we said this yesterday, you do the line integral on each component, or each subset, I guess, if I'm saying sets, on each subset of the path, and then you add the numbers. So 1 and 2 make 3. And so I have my conclusion. Now let's check. If we want to do the curl of this thing, we had set up our cross product, and you grind out the 6 products and subtract, and you see it's 0 because they're identical. So curl is 0, so there is a potential then, which we haven't found. The problem, it doesn't ask us to do that, because this problem is in 16.2, and this idea of when the curl is 0, there is this scalar function we call the potential. That's Thursday, next week. That's 16.3. But there is such a thing where this field that we're working with here is its gradient. And then if we find that, like we will do next week, and take the value of that little f at 1, 1, 1 minus the value at 0, 0, 0, you'll find that the answer is 3, which is what we've found by all this, is the what you get as the work done, or the line integral. Well, meanwhile, so what I've written here is what I was just saying. Okay, take a look at problem 19, where in the problems like this, they are telling you that your line integral is work. They're telling you what I've been saying. So they want you to compute the work done by the field moving something or other on this path. And so look at the field for 19, which is here, and then the path is given in the problem as t, t square, and t. So it's, if you thought of this as x, y is x squared, and z equals x. Okay, so if you parameterize, just as we've been doing, you see you have x, y, okay, t times t squared, is t cubed. Y is t squared minus y, which is t squared times t, so minus t cubed. Then do your dr dt is 1, 2t, and 1. And then do your dot product of this with that. And so you get t cubed. Well, okay, here I've written the dot product out. So I've copied this here, the f of t, and the dr dt. So then I do my dot product. This times that is that t cubed. 2t times t squared is 2t cubed. 1 times minus t cubed is minus t cubed. So those two cancel out, as you see, and I've factored the 2 out, and I have t cubed, which is t fourth over 4, multiply by 2, and I get a half. So I've used the word flux, which Gauss coined, and it refers to transfer of material, which could be mass, so it could be grams, or it could be, thinking of electric fields, it could be coulombs of charge, something like that. And it can either be across a curve or across a surface. So if it's across a curve, it could be units like grams per second per centimeter of length of curve. Or across a surface, grams per second per square centimeter. And as I said, you could be talking electric charge, so it could be coulombs, or magnetic induction, so it could be, well, we say Webers in this country. The German physicists certainly would have said Weber, but it seems a little bit professorish to say Webers here. So now let's look again at our maple. So this is the maple that you got yesterday, or just today if you weren't here, and you got the extra page which was missing, which is the 3rd sheet of paper in, if you were here yesterday. If you got this from me today, I have fixed it. So if you turn through to what would be the 3rd sheet of paper, the back side of that, and that'll be the single sheet of paper that I just gave you if you were here yesterday, is where we start 16.2. So you see this is getting Maple to draw the graph for us of a vector field. So Maple has the command field plot, and you see the first one is a vector where each component is a constant, 1/2, comma 1/2, and you know, for example, if your vector components are all constants, that your curl is going to be 0, because your curl involves partial derivatives, doesn't it? And you do the del cross. So if you look at the arrows, which are how you would graph the field in the plane, and you think about what we were doing yesterday, where I was asking you to imagine the water flooding across the floor and out the door, and the little ping pong ball or something like that floating in it, you see that if that's the velocity field for such a thing, that the arrows are same length and same slant, so there's nothing to make one side be turning faster than the other one as it's going along. So it would have 0, the curl of your translational velocity, which would be the vector 1/2, comma 1/2 in this picture, would be 0. So therefore the angular rotation would be 0, which we proved yesterday. If you and that's in, for those of you who weren't here yesterday, that proof is in this set of notes. That's the handwritten one that starts out divergence and curl. Okay, you should have, the 3 of you that weren't here yesterday, you should be able to find this in the pile of stuff I gave you. And so if the curl is 0, the angular rotation vector omega is 0, so the angular speed of rotation is 0. So it's, your ping pong ball is just happily floating along. but not spinning. Okay, certainly if you look at the second picture, you would expect something would be rotating, and I'm pretty sure if you actually grind out the curl of the second example that I have there, that it won't be zero. And the same, I think, with the next one. So, you see, if you're doing field plot, you type field plot and your vector, and the limits on the x and y are your limits on the size of the picture. How far are you going side to side and up and down. And then the grid is how many arrows you're going to pack into a given space. If you notice where the first one, it says 5 and 5, so if you count, there's 5 arrows across and 5 arrows up and down. And then the thickness, I think you can see what that would be, and so you can vary the thickness, and you can also put in a color if you want. If you look at the next page, the field plot YX, the color equals red, thickness is 3, and so on. So I've used Maple to try and show you how you can actually graph a field. These first 3 pages are fields in plane, but you can also do fields in 3 dimensions. So if you look at the pictures of the gradients, so let's see, I'm at the bottom of the backside of the 4th sheet paper. So there's a whole page we've gone through here that's fields that are in red ink, and then it says the exercises 1 through 4 in Thomas are fields called gradients, and so you can get Maple to work the gradient, not that you should need to. And so you see I type grad and then my function. You see that's 1 over the square root of, that's like an inverse. Well, it's, if you think of the 3-dimensional space, R from some point would be the vector x comma y comma z, and then the magnitude would be the square root of the r dot r, and so this is the kind of field that you have with an electric or a magnetic or gravitational potential, 1 over r type potential. And so if you want to plot that, you can see what you do, field plot 3D, and then gradient of, and you give your vector. You have to put in the x, y, z. You have to say they're in Cartesian coordinates, if you notice there in the command, and then your limits on x, y, z, and then your grid, how many arrows by how many arrows, and your thickness and your color. You see the kind of picture you get. And then I've done this again in red. And then problem 2, I want the gradient of the log of the square root of the sum of the squares. And
is that line 22? Sorry.
yeah, so I'm line 23, I think.
Okay.
And So you see my picture there, and then 3 and 4. So I've got Maple to do the drawings of these fields. Notice the very last thing starts at the bottom of the very last sheet of paper. The numerical value of a line integral along a path in a vector field, turn the page, in last page now, gives the work done by the field. Well, that's what we've been talking about. And finally, you see this problem 7 that, let's see, I guess that was not 7 over there. I did problem 7, which in 16.2, which refers back to these paths. So it's this picture, but it's different fields than that. So if you're doing path A, it would be the path A of the picture over there by the end of the board, but it's a different field. The field is 3y, 2x, 4z. You see how I've entered that. I have line int, vector field, 3 times y, comma, 2 times x, comma, 4 times z. And then the line, see if you're using vector calculus, you can just simply, if it's a line path, you can simply type line where you start and where you end, and it gives you the answer. So you don't have to parameterize as we did there. And then path B, line in, vector field, that's the field for problem 7, 3y, 2x, 4z. Then in a thing like that, you can say what the parameterization is, t square, and t fourth. In the book, in the directions for problems 7 through 12, for that path that is rose-colored in my drawing, they're telling you what the path is, t square, t fourth. And then your limits on t, and it gives you the number. And then if you have the 2 segments, the set union path, you can, if they're line segments like this, you can simply type line segments where you're starting, your intermediate point, that's the one, well, that's this point, and then your final point up there. So 0, 0, 1, 1, 0, and so on like that. And it tells you the total. And you could do that separately. You could do line int this to that and get a number, line int this to that and get a number, and they'll add, which is my final breadth there. Notice that the field for problem 7 is not conservative because path B gives you a different answer from path A or path C. So the curl would not be 0 for that one. Well, I think that's enough for this week, and I've kind of indicated what we're doing next week, so on. So we'll be coming back to the Green's theorem, which is section 16.4. But I was trying to put this in the context of what we're after.